Okay, so these are more examples. In this video, we will discuss more examples on how to determine the transfer functions of different systems. We focused on the electrical parts. So the first example, this is an inverting op amp because the positive is connected to the ground. So determine the transfer function of this circuit. So to determine the transfer function, we can just write first this one into this form. We can simplify these two components here and here into just one impedance, just like in circuits. So just sort of draw this. Let's call this impedance Z1. This is the combination between these two. Then this is connected to the op amp. This is an operational amplifier from your circuit, so you already know the characteristics of these devices. And for the feedback, we have, let's call it Z2. Then we go back here. This will be connected to ground, and this will be our input, V input, and this will be our V output. Because if we convert this into this form, we can actually use our derivation before of an inverting op amp. We derived this before, and we can just substitute the value for Z1 and Z2. So if we remember our non-inverting op amp from, I think this is from a second order system or the first order system. Op amp. So this is for inverting op amp. We can just replace this R2 and R1 by Z2 and Z1. So this is for non-inverting op amp. So this is inverting. This is what we want. This is negative R2 over R1. So in our case, this is equal to also to negative Z2 over Z1. And we just need to determine what is Z2 and what is. So the transfer function, now V out in S domain over the input in S domain. This is just equal to Z2, negative Z2 over Z1. But this should also be in S domain. So we just need to determine what is Z2 and what is Z1. So our Z2 is this equivalent impedance of this circuit here, these two components, and Z1 is the equivalent impedance of these two. So first, for Z1, what will be Z1s of S? So this is just the parallel combination of 5.6 microfarad and 360 kilo ohms. So we just need to convert them first into the S domain, just like what we did before. So this 5.6 here, this will become 1 over SC. So 1 over 5.6 times 10 to the negative 6 times S. And for this one, it's just the same, 360 kilo ohms. So our Z1 now, if we take the parallel combination, we can just take the admittance of the two. 1 over Z1. Then we just need to add the admittance of these two one. So this will be 1 over 360 times 10 to the 3. Or we can just multiply them directly using the parallel combination of the two impedance. So this impedance multiplied by this, so this will be 360 times 10 to the 3 multiplied by at the capacitance, reactance. This will be 1 over 5.6 times 10 to the negative 6 S, and this is all over the sum, so 360 times 10 to the 3 plus 1 over 5.6 times 10 to the negative 6 times S. That's Z1. So if we can simplify that by adding these two, so this will be, or what is 1 over 5.6 This will be 6.43 for 28. 6.43 times 10 to the 10, or I forgot to put the equal sign. All over that one is S. So I just multiplied this one with or this one I divided with 5.6 times 10 to the negative 6. All over, if we add this will be this one here. You can actually 1 over 5.6 times 10 to the negative 6 is actually equivalent to this one. 7 178 178 571 571.43 all over S, this one, so that we can just use S as our denominator, and you multiply it with 360 times 10 to the 3 S, then plus 1, so or plus 178,571.43, and we can just cancel out that S. Our Z1 now, Z1 will be equal to 6.43 times 10 to the positive 10 all over 360 times 10 to the 3 S plus 178,571.43. Next, for Z2, Z2 is just the series combination. This is just the series combination of 220 and 0.1 microfarad. So we can just write this. So this will be equal to 220 times 10 to the 3 plus this one, equivalent of this. Again, this is a capacitance. This is 1 over 0.1 micro times S. So this, we add that one because they're in series. This is 1 over 0.1 times 10 to the negative 6 times S. Here, we just add the 2 to solve for Z2. And we can simplify this. We can add them with the least common denominator S. Then we can change this instead of 1. 1 over, what is 1 over 0.1 raised to exponent negative 6.1 micro. That is equivalent to 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. 1 times 10 to the 7. This is 1 times 10 to the 7. Positive 1 times 10 to the 7. So S, so 220 times 10 to 3 times S plus this one here, 1 times 10 to the 7. That's 1 times 10 to the 7. So that if you cancel out that, it will become this one again. So that's Z2. Then to solve for the transfer function V out over V in now, you just need to divide these two. This is negative Z2 all over Z1S. So divide this with this one. So we have 220 times 10 to the 3 S plus 1 times 10 to the 7 all over S all over 6.43 times 10 to the 10 all over 360 times 10 is 360 times 10 to the 3s plus 178,571.43. And we can still simplify this. So V out over V in now will be equal to negative, what do we have here? So this what we just multiply the inverse of this, and we have 220 times 10 to the 3 s plus 1 times 10 to the 7. You multiply it with this one, 360 times 10 to the 3 s plus 17857.43, and this is all over s times this one, 6.43 times 10 to the 10 times s. So this will be our transfer function of that inverting operational amplifier. So you can still distribute that if you want. Simplify this one. Okay, so this is example number 1. Let's go to example number 2. Let's try a non-inverting op amp. So example 2. Again, derive. Let's try to derive the transfer function V out over V in. This time I will not use any given. I can just plug in any values later on, so that it's hard for me to calculate them through your calculator. So if we have a circuit, a non-inverting circuit, so we have here an operational amplifier. So this is plus and this is minus, or it should be minus here, and this is plus. So this is a non-inverting. So the positive here is not connected to ground. So this will be connected actually to our input, B input. And this will be our output, B output. Then for the feedback, so we have here, let's say, a resistor and a capacitor. Let's call them, this one is R2 and this one is C2. Then this is connected to another circuit here, another resistor. Let's call it R1 and this is C1. And this is connected to the ground. So what will be the transfer function of this non-inverting op amp? So just like what we did from the previous example, we can just write them again in terms of impedances. So this will be Z1 connected to the inverter, non-inverting or inverting, non-inverting operational amplifier. Then the parallel combination of R2 and C2 connected to the output. So this is our V out, and this is connected to the ground, and this will be our V input T, and this is Z1 and this is Z2. And again, this is minus and plus. So we already derived the formula for this, the V out of S all over V input as of a non-inverting amplifier. So let's go back to our derivation before. This is non-inverting operational amplifier. So this will be Z1 and Z2 instead of R1 and R2. And we already derived this is equal to 1 over R2 over R1, or just replace that R2 and R1 with Z2 and Z1. So this will be equal to 1 plus Z2 over Z1. And let us determine again what is Z2 and what is Z1 here. So Z2 is the impedance of this one, and Z1 is the impedance of this one. So for Z1, Z1 is just equal to the sum, R1, plus what's the equivalent impedance of this in S domain? This is 1 over S C, this C1, and this is 1 over SC2. So plus 1 over SC1. And for Z2, this is the parallel combination of the two. So this will be R2 all over SC2 all over the sum R2 plus 1 over S times C2. Then we divide this and solve for the output over input. So this will be 1 plus Z2 is, we can add that SC1. So this will be R1 times SC1 plus 1 all over, or this should be Z1. The numerator should be Z2. So I'll cut this one. Change this. So this is all over Z2, which is this one. Uh, R2 over S C2 all over R2 plus 1 over S C times 2. Then we can first simplify this before we add it to 1. So this will be 1 plus this one times this one, and this one times this one. R2 over SC2 times SC1. So S will cancel out. So this will be R2 all over C1 times C2. All over this one times this one. So this is R2 plus 1 over SC2 times R1 C1 times S plus 1. Then we can finally add it to 1. So this will be R2 plus 1 over SC2 times R1 C1 times S plus 1. Then you divide it by 1 and multiply it by 1. So just copy that. R2 plus 1 over SC2 times R1 C1 S plus 1. Then plus this 1 times divided by this one is 1 times this one. R2 all over C1 times C2. And this will be our transfer function, V out over V in. You can still simplify this again if you want. You can distribute that and multiply it with that 1 over C1, C2 here. And you can make it in terms of S squared. So this is a non-inverting operational amplifier. So this is two examples for a operational amplifier, and they will be very useful later on when we are designing controllers in control system, in PID controllers, and also for the lead and lag compensator in the last part of our courses. Okay.